All right, so in this video lesson, allow me to show an additional example about how we can find volume of a solid by accumulating the volume of the slices. Okay, and so this is the volume of calculating volume by slices method. And so this video lesson, this video example is required to be viewed after you have seen the general method, my video lecture on the general discussion about the method of calculating volume by using slices. Okay, so go ahead and view my the general discussion lecture before you view this particular example here. And then other than that, this video lesson is highly recommended to be viewed after you have understood what the fundamental theorem is. And so in that way, you can also view the video lecture of mine about the fundamental theorem of calculus before you can view this video lesson. Other than that, if you have seen all of those understanding, if you have had all of those understanding, then let's dive into the actual example. So now I'm going to turn over to the wording description of the problem. All right, so now in the wording description of our example, we want to find the volume of an object or a solid that's described as following. So just like just like the examples I deliver in the general discussion lecture video, then anytime we're doing these problems, then the problem must give us two descriptions. The first description is the description of the base region. So the description number one right here is describing the base region. So the base region is the region that's bounded by, so we have two curves. One of them is y equals 3 minus 1/2 x squared, and the other one is y equals 0. So the problem puts us on the x and y axis system, but let's not be too worried about the axis yet. Let's just see what the region looks like. So right here in example in description number one right here, I am now going to switch over to the graphing calculator of mine to look at the region here. So y equals 3 minus 1/2 x squared and y equals 0. This is a parabolic shape graph right here. So now let me quickly turn over to the graphing calculator with Desmos here. All right, so with Desmos graphing calculator, then right now in the way how it looks, the horizontal line right here is the x-axis, and this is the vertical axis, the y-axis here. And so our equation y equals 3 minus 1/2 x squared is this red curve right here, and the other curve is the other line is the line y equals 0, which is named a different name for the x-axis. And so the region, and so you can also see that the two curves here crossing each other at 2 points. We will be responsible for finding out those 2 points right there. Okay, and so the bounded region or the enclosed region must be the region where I place my mouse cursor right now inside of that. So now let me put the shading of the region here. All right, so there we go. That's the shading of the region. Okay, and so now for that region, after reading that, after having a clear description, a clear imagination of the base region, this is the base region. The next description of the problem here is the description about the cross section. But this time I want everybody viewing this video to have a closer look at this term right here. So in description number 2, every cross section parallel to the x-axis is a triangle. So the cross section, just like how I explained in the video lecture, then the cross section, once we made our stripes throughout the region, then above each stripe we have a cross section. Okay, and so the idea now is that every cross section parallel to the x-axis is a triangle whose height and base are equal. Okay, so I will get to this a little later, but for now let's understand what it means by every cross section parallel to the x-axis. So this is a little bit different. This is a little bit different with how it has been throughout the two examples I deliver in the general discussion lecture over here, because most of the time we see that the stripes are perpendicular to the main axis, but here the stripes is parallel to the x-axis. Okay, and that's what I was always trying to emphasize earlier. We will decide the major axis later. Right now it's just whatever it says parallel to the x-axis. Let's just draw it that way. So now back on my Desmos right here. This is how we see the stripes. So as we already know, every cross section is a picture that's erected above the stripe. So this is now what the stripe looks like. So the stripe must be parallel to the x-axis. So the x-axis is here. We placing the stripe being parallel to the x-axis. But so think right now in the way how the picture is being parallel to the x-axis means each stripe here must be perpendicular to the y-axis. Okay, so again, since every stripe here, because the each cross section is described as parallel to the x-axis, so consequently each stripe must be parallel to the x-axis, and consequently further each stripe is perpendicular to the y-axis. That's the ultimate goal that I want to see right there. So each stripe here is perpendicular to the y-axis. So in that way, in the way how we have been chosen, in the way how I have been emphasizing, let me make a quick sketch of the picture. I will put the final sketch of the picture on this board where I'm at, but right now let's put on a scratch version, a scratch sketch. So in the way how we are seeing right now, here's the parabola that's pointing down, and every stripe is parallel to the x-axis. So the x-axis and the y-axis are the two axes that the problem talks about. Right now that's the problem talks about, but in this problem, allow me to explain the following. Since all stripes are parallel to the x-axis, and now in the way it is, we understood, I explained earlier that each stripe here, or every stripe, is perpendicular to the y-axis. That means in this problem right here, consistent with how I have been explaining that throughout the entire general discussion lecture with the two examples there, then here we want to choose, in my experience of teaching this problem right here, we want to choose the major axis, because in the way how I have been teaching them, among the axis, there's always a major axis. There's always a major axis where we can measure where the thickness and we formulate the stripes length and area of the cross section based on the major axis. So in that way, the major axis is indeed this y-axis right here instead of the x-axis. Okay, so the term here was a little tricky. Every stripe is parallel to the x-axis. So that gives us a clue that the major axis we're actually doing here is the y-axis here. So y-axis is the major axis. Okay, allow me to use that term right there, the major axis, in a sense that it's the axis where all of our expression is going to be in terms of y. Okay, the thickness will eventually be dy. We will get to that, and then the cross sections, the area of each cross section will have to be in terms of this axis right here. Okay, and so now that we have agreed upon agreeing that the major axis in this problem should be the y-axis, simply because the y-axis will be perpendicular to every stripe that we are drawing in here. So the stripe is being described as required in the problem, but then from there we identify our major axis. But now allow me to show this trick right here that's making life even simpler for us. Okay, so right now the stripes are looking parallel to us like this. I mean, looking parallel to the x-axis, and of course our mind is very naturally attached to the x-axis as the major axis. But as I argued earlier, this is now the major axis being the y-axis. So in that way, to make life easier for us, why don't we turn the picture here, the exact picture here? Because the picture is just a picture. So why don't we turn the picture, why don't we rotate the picture here in a way that's making it easier for us? Okay, so now allow me to show that this other picture here with the computer on that mode right here. So this is the original version. Okay, this is the original version. The y-axis right now is still vertical because that's the way right now where each stripe is perpendicular to it, because each stripe is parallel to the x-axis. But now have a close observation here. I'm gonna purposely rotate the picture so that now here's how I'm seeing it. The major axis is still here, which is now, guess what? The y-axis is now turned into the horizontal axis here, and the vertical axis this time, we can call that the x-axis, and the positive direction of the x-axis is going in the up direction right here. Okay, so this is the y-axis, and this is the the vertical axis. So now in that way, it's easier to see the stripes. Still those same stripes, but now they're all looking vertical to us. They're all looking vertical to us, so that all the stripes here, are perpendicular to the x-axis. I mean to the horizontal axis that we can see clearly right here. So our major axis now is the horizontal axis here. So it looks like, and it's actually it also came up from my own personal experience that I prefer doing it that way. It's easier for me to see the major axis being the horizontal axis. So I'm trying to pass down that experience to students or viewers who are learning this. What kind of problem would be like that? Okay, and so in that way, now I am going to sketch the actual version. I am going to actually sketch the final version that we're going to be doing the work with here. So our major axis is this horizontal axis, but we name that, it's the y-axis. Okay, and so, and in the way how the picture looks, the x-axis now comes that way and allow me to draw that, sort of like to mimic, to make it similar to a 3D version right here. So our shape becomes like that. Okay. All right. So each stripe that we're doing, yes, each stripe we're doing is perpendicular to the major axis here, being the y-axis. All right, so that's the idea like that. So yes, now it's easy to see that there's a thickness for each stripe, and then we're gonna build some kind of shape over on top of each stripe here. Okay, so let's say if I have a stripe here, there's a shape. Okay, if I have a stripe here, there's a shape being built on top of that. Okay, and all the shapes or all of these stripes are parallel to the x-axis, but see, the x-axis is no longer our major axis, and that's a little bit of hopefully a good trick that the students who learn this with me can pick up from that. All right, so now let's have an understanding. Let's have some understanding of the cross section a little even further. So now let me get to that wording description of the cross section. Okay, so every cross section parallel to the x-axis, we nailed that down. Okay, so now let's look actually at the shape. So every cross section is a triangle whose height and base are equal. So this is such a little looser definition right here. It's a very looser description because there are so many various situations that can happen here. Allow me to explain. So now back on the board, let me just extract out any one stripe and put it right here in front of us. Imagine that we are looking straight at the stripe. So if we're looking straight at the stripe, and imagine the stripe is right here horizontally right in front of us, and we're looking straight at it, our eyes is going in and looking at that. A triangle whose height and base are equal. So we are expecting a triangle, but this is the base. The stripe here, the stripe that's right on the region, on the base region, is becoming the base of the erected triangle above that. But the requirement here says base and height are equal. Okay, so the height here, the base here, I mean the height and the base. So we can have a picture like that. We can have a triangle that looks like that. See, I'm trying my best to draw the height and the base being equal. But that's just one version, because there are so many places. Just knowing, and that's the reason why I said it's such a loose description right here. The height, yes, admittedly being equal to the base, but we can put that height in so many different places. We can have a different version, same description, but we can have a different version. How about I can put the height right there and the base, and now that becomes a right isosceles triangle for us. The height and the base are equal height, and we can even put the height, it's the same base here, same stripe. We can put the height the other way around, so that we can have a different isosceles right triangle. Height and base are equal. Okay, or we can even put, if the stripe is here, we can put the height there. So it's a different triangle, no longer an isosceles right triangle. So the point now is that whatever shape that we choose here, but make sure it's one shape throughout all. It could be a triangle like this. It could be a triangle like this. These are all satisfying that requirements about the height and the base are equal. But whatever we choose to draw our picture, make sure to stay in that same shape chosen for all stripes. So all stripes have to follow the exact same shape chosen. For simplicity, and due to the limitation of my computer software that I'm about to use right here, I'm going to choose either one of this. Okay? I'm going to choose either one of this. So now let me bring up that surprise for everyone. Because these are all, again, as I argued earlier, and the point now is that it doesn't matter which shape that is. Once we've done getting the volume, it's gonna be the same amount of volume. That's the good part about that. Okay, and so the description was such a loser description, but in the end, it's gonna turn out the same result. We might have different people, different shapes, different solid shapes coming out on different people like that. But in the end, it's all gonna be the same equal volume like that. Okay, say, if I'm a student working in class and the guy next to me is doing this shape, whereas I'm doing this shape on each of my cross section, we're gonna have different solid shape, but the volume will be the same between us if we both follow through the correct orientation. So now allow me to show that on the computer graphics here. All right, so this is the version of the region where I put the major axis being horizontal, just as I argued earlier. So this is the y-axis here being the major axis, and all the stripes are here being perpendicular to the major axis, just like how I have been describing it. And so now, according to my version of the software, and like I explained earlier, this software is limited to using, isosceles right triangle. But if we're looking at each stripe right here, then it puts the right angle on that end right here. Okay, and so that means in the way how my shape is, it's consistent with this picture of mine right here, that I'm using this version. Okay, so that means in the way how I'm drawing, if the stripe actually shouldn't matter. In the version that I'm drawing, then at any stripe, okay, I am going to draw my rectangle like that, my triangle like that. Okay, the right angle is right here. Okay, so we have another. So the major axis is actually this one here. Okay, and then our triangle is like that. All right, it's a little hard to see in my 3D picture right here. That's why I had to bring up the 3D animation that you have seen earlier. All right, so now once we've had all of that, then we are ready. Once we agree with the way how the picture looks, right, and agree with the way how I place my major axis, then the calculation work will come out easy. So on any of the stripes being at the foot of the cross section, we have a thickness. Okay, so there's a thickness. Okay, so that's the way how we see the thickness in each of these stripe here, in each of these cross section. Okay, and now you have a clear picture of how the thickness should be measured. And so now again, let me remind anyone doing this problem here the fundamental, the understanding. All we need here is to calculate, to figure out a formula, to figure out a general representation of our slice area, or the area on each slice. Then we multiply that generalization of our slice area with the thickness. So thickness times the area of each slice right here gives me the volume of one slice. Okay, and again on my picture here, see, hopefully it's big enough as a picture for everyone to see, but it has, every slice has its own thickness, just like the way how I'm putting it, so that you can see there's a thickness of each slice. Okay, and the area of the cross sections is out here. Okay, on each slice like that. All right, so now in that way how I'm seeing it, then that's the volume of one slice. So now an integral, when we're applying a definite integral, an integral is accumulation of all these slice volumes from a start to an end. That's the only one fundamental I repeat for myself in every problem I'm doing. Think about back in the days when I was still a student myself doing this problem. once I click with that understanding, I only stay with that fundamental idea, with that fundamental goal right there throughout any problem about calculating volume using slices. Okay, so that's the fundamental. And so now in my personal experience that I want to pass it down to my students, I would start out by identifying the thickness based on the information we have. So now we understand that we put our major axis to be the y-axis here. Okay, then immediately it makes perfect sense. It makes perfect sense that thickness has to be a dy. And like I said, we set with y here simply because the problem gave us the y-axis and the x-axis and all that, but in reality, this the name of the major axis can be whatever. Okay, now I want viewers and students of mine to understand this axis here where we measure our thickness here as the major axis. It's the axis where one big characteristic is that it's perpendicular to every stripes throughout the region. That's how we're doing it. All right, and so now if the y-axis here is being our major axis, the thickness is dy. So now we will be ready for heading out our way to identify the area on each slice right here, the surface area of each slice. And let's have a look. Okay, so now I am going to navigate to my other board, and let's have a picture of that. Okay, and so the curve itself. Right here, the curve itself is represented as one curve. It's represented as y equals 3 minus 1/2 x squared. This is one curve, one parabola. But now we're not working with a picture in this orientation. And you can see that the curve is expressed as a function of x right now, not what we need. Because, and I should have also mentioned, once I have decided that the thickness is dy, then just like how I have been doing that throughout the examples in the general discussion lecture, I am going to revise this formula, this fundamental idea here, but replacing the thickness here with that dy. So that tells me a goal that in the next step is getting the slice area, the area on each slice, I have to express that in terms of y. This has to be in terms of y, because to make it consistent with this dy expression, that's what we need. Okay, and then it's from a start to an end. So everything is becoming consistent with each other. That's in the sense that now once we decided that differential dy here, then the expression here has to be in terms of y. And it makes sense that since now our stripes, in the way how it looks right now, our stripes are stripes that's being limited by that curve, that upper part of the curve, and that bottom part of the curve, and the major axis here is being the y-axis. So we have to express our stripe here as a function of y, because each one of our stripe is the length of our stripe here should be determined, is currently being placed at a y value on the y-axis, on the major axis that we call the y value. How's that? Okay, so in that way, now even though I'm only having the current picture here on the board here is that the original version, but now we have to think for ourselves. We have to rewrite this equation in terms of y. Here we have to re-express that equation in terms of y. And so now if we rewrite this picture, if we redraw this picture to have the y-axis going this way and the positive x-axis going that way, then the picture looks just like that on the from the computer screen. So now how do we write this same curve? Because this same curve right now is y equals 3 minus 1/2 x squared. But how do I write that same curve to express that in terms of y? Okay, right now it's y equals 3 minus 1/2 x squared. But we want to re-express that to be a function of y. So algebra work again. Y equals 3 minus 1/2 x squared. I am going to add the x squared term to the left and bring that y term to the right hand side. So here I'm looking at 1/2 x squared equals 3, and I shouldn't write that minus 3 here. It should not be there. Okay, and so it's equal 3 minus y. And I'm going to simply and algebraically multiply 2 from both sides. So I'm looking at x squared equals 6 minus 2y. 6 minus 2y. And then I'm going to take square root on both sides. And I will get, just like how I have always been telling anybody in other video lectures throughout my time studying with me. Anytime we're taking the square root on both sides of the equation, we have to do the plus and minus square roots. So now we have two square roots. Okay, 6 minus 2y, positive square root of 6 minus 2y, and negative square root of 6 minus 2y. All right, so why is that? All of a sudden, when we're writing things in terms of y, for this problem, we're running into two curves. Yeah, it makes sense that way. Think about it. We can break the curve, the same curve, but we can break that into now, because since we're putting the axis this way, one curve is above on the positive x, and the other part is on the negative x right here. Positive x and negative x. So that's why there's a positive square root of 6 minus 2y. That's this curve right here. So now I can label this curve. The positive side, I can relabel that. This is x equals a positive square root of 6 minus 2y. Okay, and then the bottom curve right here is, it looks like in the way how the picture is oriented. Then the bottom here is that curve x equals negative square root of 6 minus 2y. Now we have two curves. And so now, how do I see the stripes here? The length of any stripe. The length of any stripe is determined or is limited by the upper curve subtract the lower curve. It's just the difference between upper curve and lower curve here in the way how we place our picture. Okay, so I'm trying to make the problem here just like any of the problem we have seen on standard, right from the examples already delivered in the general discussion lecture. So pretty much from my experience right here, I found to myself successful anytime I've always put the major axis to be the horizontal axis. Okay, so yes, we have to trade off with a little bit of work to solve the variable in terms of the other one, for one variable in terms of the other one, but then in the end it will be easier in the sense that we put ourselves back into one convention that all of the stripes here have to be perpendicular to the major axis, and the major axis here is it's easier for me at least, so I'm trying to pass it down for anyone. It's on the horizontal line right here, and that's the idea. Okay, so now in that way, here's how I see it. So allow me to erase this algebra solving work. We take both, right? Again, just like how I label here, upper curve is a positive 6 minus 2y. This is negative square root of 6 minus 2y. But the length of the stripe is between, as a difference between the two curves, upper curve minus lower curve. So now, and once we build that triangle on top of that, then this is just the base, okay? And so now here's how I'm seeing it. All right, so we have upper minus lower. That gives me the length of the stripe. So here the upper curve here is clearly speaking square root of 6 minus 2y minus, and then there's the other one, square root of, and it's actually minus, and I have to put things in parentheses, negative square root of 6 minus 2y. That is this is a generalization of the length of any stripe depending on where we put the stripe at any y value. That's how it is. And the y value, just think of that as in this problem it's called a y value. In the other problem it could be the u problem. It could be the u value, but wherever we put that on the major axis, wherever we put our stripe on the major axis, okay, and that length right there is measured in terms of the variable of the major axis. All right, so now, as a matter of fact, simplifying down this expression a little more, the length of our stripe, of each stripe, will generally be determined by, see, that's minus, but with a negative, so it becomes a plus. So it's 2 times square root of 6 minus 2y. 2 times square root of 6 minus 2y. So this is the formula for getting the length of the base, okay? And now, once we're erecting our our triangle over that, remember, base and height are equal based on the description, according to the description. So the area here now has to be a function of y. Okay, the area of any triangle is 1/2 base to square root of 6 minus 2y times height, which is another 2 which is another 2 times square root of 6 minus 2y. Because why am I using the exact same expression here? Because the description, the description of the cross section said that all we need is a triangle where base and height are equal. All right, so in that way, here we go, formula. I mean the area of each cross section as described. Okay, so it's a 1/2 base times height. And so now we can do a little bit of algebra here. The 2 here cancel with that 2, that left behind with that 2 right there. And then we're going to end up with the square root of 6 minus 2y all square. So all together, really, we're looking at, now I can swing back to my other board. Slice area, or the area of each slice, is going to be a 2 times the square root of 6 minus 2y all square. That came straight out from the other board that I worked it out. And now it's even better. The 2 cancel with that square root. I mean the square here cancel with that square root, but maybe let's get that done when we set up the integral. But this is the final, the description of the slice area. And now we're ready to fill it in. So now in our integral over here, and it is going to be 2 times, okay, that's a square. Now inside of that, square root of 6 minus 2y. See how simple things can get sometimes if we know how to effectively do the work. And so now let's look at the start and to the end. So it looks like in the picture. So now let me bring back that picture on Desmos calculator right here. So this is how I place my slice, so as everybody agrees with that. So it looks like in this way right here, then the slices, right, or the stripes or the cross sections are being accumulated from the left to the right, okay, of the picture. And so the left here, it starts at y equals 0 and ending at, okay, so let's see what this value is, okay. All right, so this is where it ends. Keep in mind, this is the y-axis. So let me for once more time switch back to the other version. So you see, this is the high peak of the downward parabola. This was the y equals 3 minus 1/2 x squared here. So imagine once our stripe hits to the top right here, that value has to be y equals 3 here. It has to be y equals 3 here. Okay? It has to be y equals 3 there. So that means what? Our right end of this region has to be y equals 3. Remember, the vertical line here, the line perpendicular to this axis has to be y equal, okay, because we place our y-axis on this side right here. So y equals 3 is this top, this right end right here. All right, so now that means in the picture, I'm ready to fill it in. Start of the accumulation is at y equals 0, and the ending of the accumulation is at y equals 3. Now, ladies and gentlemen, we have completed our setup for the integral that can calculate the volume of this solid right here by accumulating the volume, slice volumes. All right, so now in that way, I am going to, once we've had that integral successfully set up, I am going to use the fundamental theorem of calculus and get things done here, get the integral evaluated. That's what gonna be. That's what's waiting for us right there. All right, but now I'm going to use a little bit of algebra. So instead of doing that here, I just want to show the final understanding, the final putting together of the slice area. But now we can take advantage of some algebra. 2 will cancel, I mean that square power will cancel with square root. And that 2 here is, all of a sudden we realize is a constant coefficient. So now allow me to erase this. And our integral, before we actually do the fundamental theorem of calculus, we can rewrite our integral as 2 times, in front of the integral, 2 times the integral from 0 to 3, okay? Square root, as I said earlier, cancel with the 2, I mean with the square, so now we'll have just 6 minus 2y and dy, and shockingly, we turn our problem into a very simple problem like that. And so now this is where fundamental theorem of calculus comes in. We're looking at finding the antiderivative of 6 minus 2y. So that gives me, and don't forget there's that constant coefficient too. So 2 times 6y minus y squared, and allow me to assume anyone watching this video is fluent enough with how to find antiderivative there. And I'm going to go ahead and evaluate this antiderivative from 0 to 3 like that. And that's making the problem a lot easier. All right, so in that way, here's how I'm seeing in the next step. Fundamental theorem of calculus say I am going to substitute each value here. But since the bottom one here is 0, later on it's all just 0 out. This 3 substituted into the antiderivative gives me 2 in brackets 6 times 3 minus 3 all squared. That's the antiderivative evaluated at x equals 3. And I'm going to subtract out a complete 0 out due to 0 substituted into this antiderivative. And so with a problem like this, now it's surprisingly simple that I don't even need to step over to my computer station to get an answer right here, to get a numerical answer. It's quite ready right here. So that's a 9, and this is an 18, right? So 18 minus 9, that gives me a 9, right? And multiply with 2 again. So that's now comes up with a total final answer, positive 18 here. All right, so positive 18. So that is the end of this particular example. The specialty of this example I would like to bring up is that we got 2 little specialties here. I want you viewers and students of mine to understand that a lot of time we have that control, because once I just need you to when you're doing a problem on your own, you just simply need to be able to identify where it should be the major axis. Okay, and so I already been telling clear about how to identify the major axis. The major axis. In my experience of doing these problems, and I'm trying to teach it down like that, the major axis is, keep that as a key characteristic, is always going to be perpendicular to every stripe. So whatever the stripes being described in the problem, the stripe that we stripe through the region, but major axis has to be always perpendicular to all stripes. Okay, and so now once we identify, so sometimes the problem can turn out x-axis to be the major axis, or the vertical axis to be the major axis. But once you identify where the major axis, the next specialty of the problem is that you have your choice to turn the picture around to make it easier. And at least for my experience, it was easier for me to get it done like that. Okay, so instead of the original version, the region looked like that, and the stripes went, of course, parallel to perpendicular to the major axis right here, but it looks parallel for us. But now we had our choice to turn it sideways so that the major axis now is the horizontal axis, making it easier for us doing the work, and we see that consistent with our understanding that the stripes, each stripe here being the base of each cross section, is perpendicular to the major axis, and that's the specialty that this example carry right there. And then so because of that work, we will need to spend some time consequently doing some algebra to solve for, in case it did not come out as an expression in terms of the major axis, then we have to do some algebra, right? And sadly I erased that here, but you have seen that work earlier. And that's the specialty, the 2 specialties of this example that really deserves its attention for any students working through these kind of problems. Okay. And then just a last specialty, but it's not as important, is that we actually have a choice of choosing the shape right here. Like I pointed out earlier, the description of the cross section was a little loose description, but in the end we're still going to end up. So I pointed out that just simply describing the cross section here as some triangle having height equal and base being equal. We can have quite a few different varieties. Okay, so I recall I explained earlier that here's the base, right? Then we can put the height like that to be equal with the base, and we have consequently a triangle like this. Somebody else other than me can approach the problem that way. It's still going to be the exact same result. How you come up with this? How you come up with this area formula of each slice right here, or in my picture to assist our visualization, I use, and my software that I used was only able to give me, see, from where the base is, right? Base with whatever length that is, right? We can come up with a triangle being like that. Base and height are also equal. So we have quite a few different varieties like that. Okay, and so but it's still going to give us the same final numerical result. And that's a specialty about this, so that anyone learning through this example can also be aware that, you know, when you're working with a problem like this, right? Then what matters is how you understand about the cross section.